you have any question, feel free to ask. Is everything clear so far? Okay, good. So as you know, today we are going to talk about the temporal differences, TD, learning. We will start to see how it is working, and we will see a couple of algorithms today. We have many different topics to talk about temporal differences, and we have the core algorithms of the reinforcement learning in this topic that I wished we could cover all today, but I'm afraid we cannot. We need more time. Because of that, today we are going to see just a couple of them. Then next lesson we're going to continue. But let's break it down and see what does it mean, and what was the problem that we had already and what we are going to improve. So just making sure that this is working. Okay. Okay, good. So we are talking about temporal differences learning, TD learning, as one of the most important topics that we are going to use it a lot later in future too. The advanced algorithms are also mostly based on this topic over here. Today we are going to see the most general basic concepts, and later we are going to continue with the most important algorithms of reinforcement learning that afterward you even can start your projects based on that you will able to almost solve all simple problems with it. Then we continue with making it more complex and comprehensive to solve complex problems. So in this chapter we have the temporal differences learning algorithms, the basic concepts. Then we will talk about the temporal differences 1, and we will see what is the differences between the previous algorithms that we've talked, dynamic programming, and also Montecarlo approaches. Then we will talk about the temporal differences 0. We will see what's the differences of the 1 and 0 quickly. Then we went through temporal differences lambda, and there are multiple approaches. We will see one of the approaches how we can solve the temporal differences lambda. After that, I will introduce the SARSA a little bit, one of the algorithms that you can use it to solve reinforcement learning discrete problems. That we continue it later with famous algorithms that like the basic most important algorithms like Q-learning. So first of all, let's talk about the temporal differences. We say TD learning is class of model-free reinforcement learning. So what was the model-free reinforcement learning? We had the model-based and model-free. When we declare that we don't have transition probabilities and we don't have the reward model in advance, we have model-free reinforcement learning, right? So we don't know dynamics of the environment, we don't know what's the probability of this event occurs or that event occurs, so that we have also model-free reinforcement learning. The name temporal differences comes from using the differences or changes of the value that we have. So the name almost declares what we are going to do. It is kind of like we are going to care about the differences of the value that is happening during time. So far we've learned different equations, different terms, how to calculate the value, but mostly we calculated, especially in Monte Carlo algorithm, the whole episode in order to do something. But here, we are mostly going to focus on the change during time and try to improve during the events that is happening or each step of the episode. So the differences is to use, as I explained, in the learning process based on the reward signal. So agent do something in the environment, the agent gets the return, gets the reward, then based on that reward, we can update the value, that update of value gives us some change. And this change is important for us in TD learning. So we can declare that TD learning is a combination of the Monte Carlo and dynamic programming indeed. Now you should think how you can load in your mind what was the Monte Carlo, how was it working. We saw a couple of algorithms for it, and dynamic programming, how was it? And I give you a few seconds to think about it, how TD learning can combine both of the benefits of those algorithms. So we say, okay, like Monte Carlo methods, the TD methods can learn directly from raw experiences without model of the environment. I already mentioned to you, so it is model-free. When TD learning is model-free, it means that we don't need transition, probability, and dynamics of the environment. Actually, we don't want to give a lot of information to agent. We just say, okay, this is the environment, and work and interact, get reward, and learn what to do. So based on that, it looks like Monte Carlo approach. But on the other hand, how it is looking like dynamic programming? It looks like dynamic programming based on the part that, so we say TD method updates estimate based on the part on other learned estimates without waiting for final outcome. If you remember, in update rule of the dynamic programming, we didn't need to wait until end of the episode to update the policy, for example. So that in that term, since we can update during each step of the episode, we can call it as similarity to dynamic programming. But this process of using part of other learned estimation can be called bootstrapping, that we have in detail this slide that I'm going to explain it well in detail. What does it mean, bootstrapping, better. So what is the relationship between temporal differences, dynamic programming, and Monte Carlo approaches then? So many algorithms we've learned, or we are going to learn in this chapter. We say all of them are the approaches that we are using in order to solve reinforcement learning programming in different ways. So some of them have benefits over each other, of course. We are going to talk about also compare them to see which one is better in which kind of approaches. And of course, in advanced algorithms, we can have benefits of all of them together or combination of the benefits. For example, as you can see, TD uses dynamic programming and Monte Carlo approaches benefits together. So let's say if we want to have a look at the general differences between temporal differences and Monte Carlo methods, so before understanding that, clarify, okay, how they look like generally. In Monte Carlo methods, we said that they are learning from experiences. If you remember, we were sampling episodes, and based on that sample of the episodes, we were updating what we want. Last week, we've seen many examples of this. But also, temporal difference learnings are based on the experiences too. It means that, so why we have experience? Because we don't have model of the environment. So since we don't have model of environment, we need experience. And here, just the difference is like, it should be or it can be limited. We don't need to have the experience of the whole episode in order to proceed in temporal differences. So based on this concept, we say in Monte Carlo approaches, the algorithms must have wait until the end of the episode. But here, in Monte Carlo, in temporal differences, we can learn before knowing the final outcome. Monte Carlo only works for, therefore, episodic problems, but temporal differences can work with infinity horizon. Why? Because it was challenging, or it is challenging, if we have infinity horizon over here. Because if we have infinity horizon, as you saw, we need to generate whole episode. But if there is no end for the episode, what we're gonna do? So that's a challenge there. Based on that, Monte Carlo approaches are mostly known for episodic problems. But on the other hand, temporal differences can work with infinity horizon, so that we can have a small part of the time to use the time to update the rules, update the values that we have. So this is a clue that later on, when we are going to talk about more advanced techniques, we will see that temporal differences can do better job in continuous environments too. So similar to previous algorithms and techniques that we've talked, here also we have two classes, temporal differences prediction and temporal differences control. Temporal differences prediction states for prediction of the policy that we have. You may have policy that you wanna evaluate the value of the policy that you have, how good your policy is. In simplest way of understanding, if you have two different policies for a problem, you can compare them by assigning values for them. But also there are pretty nice applications, so that, for example, in trade market, you can evaluate the policy that is running for selling and buying, and you can evaluate how good the policy that I'm running is, and compare different policies of buying and selling rules that you have. So TD prediction. On the other hand, we have TD control to solve different kinds of problems. In TD prediction, we are going to see three different techniques, three different algorithms. Actually, two of them are very simple almost, and the third one is a little bit, we need to know some parts that today we are going to discuss three of these. Temporal differences 1, temporal differences 0, and temporal differences lambda. But on the other hand, we have the TD control, that those are very handy and useful techniques to solve reinforcement learning problems. Also, we have famous ones, like we have SARSA, that is on-policy TD control. We have Q-learning, off-policy TD control. And we have expected SARSA, that both can be on-policy or off-policy. What is the on-policy and off-policy? I'm going to clarify for you 100% in the next chapter that we are going to talk about these three. And also we are going to see how they are especially working, and we will solve pretty nice problems with these techniques. Just pre-note that, of course, this Q-learning is one of the most important algorithms in reinforcement learning. In whole course, if you learn this well, so that's kind of big step for you, because that is the basis of most of the advanced algorithms based on the deep reinforcement learning techniques that we have. All of mostly the concept is coming from Q-learning. So, any questions so far? Today we are going to talk about these three. Then you will have some practices. Then those three of them together we will talk in one lesson. So let's dive in TD1. TD1 is again for estimation value pi. So we want to estimate the value of the policy that we have in TD1. Actually, it makes update on the value that we have at the end of the episode, similar to Monte Carlo, but the difference is that we are not limited to. It is not like a must. It can be end earlier. But basically, the general rule says that we want to update the values at the end of the episode that we have. Therefore, as I explained to you, we can stop for any reason that we have in continuing tasks based on the TD control. So in episodic Monte Carlo techniques, we say that we cannot stop it. We should calculate the episode, because the equation says, okay, you need to calculate whole episode in order to be able to update it. But here, we can still have some releasing on that part. So it is similar to Monte Carlo to use the experiences to solve the prediction problem, but in online or any step fashion can be run too. It is also well known as, if you look at the literature, you may get confused, but because they are very similar to Monte Carlo implementation, because of that, TD1, also known as the way of the Monte Carlo implementation, also in literature is known in this way. So what is the reason? The main reason in mathematical form of similarity is calculating of the GT. If you remember GT, we had the GT, that is the return in time t, that we calculated by giving the reward at time t, the reward at the moment, then discounted reward at t added by 1, then discounted reward at t added by 2 up to end of the episode that we have. And this discount factor was to giving the importance of the reward based on the time that we have. So the discount factor is the to the power of the, for example, time 1, 2 up to t minus 1, so that it is decreasing the importance of the reward that we are getting in the future, and now current state's reward are more important. So based on that similarity, keep that in your mind, GT. Now we want to use the sum of the discounted rewards from whole episode and kind of calculate the TD error. What is the TD error? TD error is over here. So we say we can calculate the value of ST, value of the state t, by adding the value of the state t by the differences between GT and the value of the state t. So when we are talking about the temporal differences, you should always think about this part over here. So the differences and temporal differences, that based on the time, we're getting the amount of change that is happening based on the value that we have. So here we have the value ST that is called as the previous estimation. So we have the updated estimation here that is coming from the the differences between the GT and the value of the ST, and the alpha as learning rate that shows us how much important is this new update that we have or the old value. So if this has like big, the alpha is learning rate, or usually value is between 0 and 1. How big it is, the step size of the updating of the value of the ST is bigger, so that our algorithm will try to learn the values and update the values with bigger steps, move toward the optimal value that we have. So is it clear for everybody? Any question? So in temporal differences 1, we need to again calculate the GT, similar to previous examples. After calculation of the GT, we get the temporal differences of the GT and the value amount of the change that we have, just by simply subtracting them and calling that part as TD error. So this is the whole algorithm. I didn't show the algorithm detail because it's quite similar to previous techniques that we have. Just you need to do the same procedure, but this time change the update rule by the value. Then, what about the next technique? What about the temporal differences TD0? By understanding TD1 and temporal differences concept, we're gonna see that this is also okay, not complex, almost simple idea. So again, we are in prediction technique. Based on prediction technique, we have policy, and based on the policy, we are going to compute the value of the policy that we have. To do so, actually, the idea is, okay, let's get rid of waiting for end of the episode or calculating to the end of the episode. Just whatever is happening by temporal differences currently, let's consider that to update the value that we have. That is in contrast to Montecarlo methods. So how that is working? Basically, we're considering applying the action and move to the next step, then update the value. How it looks like? In general, looks like we have this state. We do the action, go to the S prime or next state, and we're gonna update the value of the previous state. So also we call it as one-step temporal differences, known as in literature. If you have a look, we call it as TD one step. What we need to do, simply, the same equation that we've had for TD1, find it in your mind. That was value ST is equal to value ST added by the learning rate, GT, and the VST. Now we need to replace this GT with what? With this term over here. Simply, what we do, we say value of S is equal to, again, value of S added by learning rate, the reward S prime added by the gamma value of the S prime. So, actually, gamma value of the S prime subtracted by value of S. So, instead of considering whole GT, this time we are going to consider the discounted value of the S prime. It is like, in order to update like S to S prime, instead of calculating whole episode to update what I have here, I just consider the differences of the movement, and differences of the what is happening based on the value calculations, and updating my value. The idea is pretty simple. So that we can say immediately on transition S prime or ST plus 1 and receiving the reward that I indicated in two terms. We sometimes, as I mentioned to you, we can use both S prime or ST added by 1, meaning the same thing. So is the term clear for everybody? Any question? Again, we have discounted term, discounted value that we can discount, but only for one step. So in order to implement it, again, same procedure, similar to Monte Carlo, but the update rule of the value is changed. And only one step differences ahead. So here, for temporal differences 0, I've shown the algorithm for the prediction that you can see. So if you want to have a look together, we have the input, the policy pi that we want to evaluate. So we have the problem. For that problem, we get the policy, and we want to evaluate it. First of all, we consider the algorithm parameters, like the step size of the alpha, that can be between 0 and 1, and how fast we want to update the algorithm that we have. We initialize arbitrary value of the S for all states, except the terminal ones. So when you are going to run the algorithm, if you remember in Q learning, in updating the Q values, we said that it can be 0 or arbitrary value. For the value is the same as the examples. We can put zeros or arbitrary value. Later we have a loop that for each episode, first we initialize the state, and per each one of the steps in this episode, what we do, we take the action, and action comes from where? Action comes from the value, the policy that we've had, the policy that's given to us, not generating with epsilon greedy or something, just directly comes from the policy that we have. You may think, okay, the action comes from policy, and maybe the policy is like stupid and it has loops forever or something. What happens then? So of course then your policy is bad, and the value evaluation will be totally wrong or something very bad. Okay, that's the point that in implementation you may face. So based on the action that taken from the policy that we have, what we do, we run the action in the environment or in the simulation, then observe the reward and the state, next state. Then we update the rule, update the value, the same equation that we discussed. Value of the S is equal to value of the S added by the learning rate of the reward added by the discounted differences of the value ST plus 1 and the value S. So the differences of the next state and current state, value of the next state and current state will be TD discounted added by reward and will update our value. The whole thing that is happening is pretty simple there. Then of course we update the state to the next state and loop this to compute temporal differences TD 0 here. Is it clear for everybody? Any question? Question? No? Okay. Good. You're going to implement this today. So now let's have a look at simple example to see if we really want to do some coding and implementing what is going to happen. If you consider random walk example, in random walk example, we can have an agent that randomly walks to the different directions in 1D to the left and right. And we want to find, for example, to go to the end of right or go to the end of left in order to find something or get reward. And if you want to apply on that algorithm, let's see what happens. So we have two actions, left and right, with random walk. You've solved also similar examples with other scenarios. Episode can terminate in left and right if you want to talk about random walk explanation, and it looks like this. We have this start, very famous, simple problem for reinforcement learning, basics understandings. So, for example, let's say agent starts from here, and our algorithm technique was to, for example, get the reward when ends up at the right. And in here, for all the other states of the movement from C to B, B to A, or this terminal state, the agent doesn't read anything, doesn't receive any reward from the environment, just only being at the end, right side will have the reward. So we want to see empirical comparison of the prediction ability of the TD0 and Montecarlo. Let's have a look how they looking like if we want to run it. So we have the problem over there. And here we are showing the estimated value that, that with running different numbers of episodes, what is happening. So if you look at this black line over here, partially is red, but this black line, consider it is 0. What does it mean? This indicates that for state A, B, C, D, E, we have values of 0 per each one of the states. We initialize 0 in this particular example, right? Just don't look at the other ones for now, just consider 0, 0, 0. So here, the value initialized as 0, and that's the plot that we have. So what is the true value? Or maybe not better, let's keep it to the end. Of course, we have true value here. But if we consider the updating temporal differences algorithm and technique with TD0, after one episode of running, you see that it is changing over here. After 10 episodes of running, you see that the plot is looking like this. The values in the right side is increasing, and the values in the left side is decreasing. Why this is happening, do you think? Because of the update rule of the value that we studied, and that comes from where? Comes from this real environment. If you look at the state C, on the right side we have reward 1, and this reward 1 says to us that, okay, our agent, if goes to the right, should be better. And it's supposed to be values of the right side states higher. That's the reason in the plot that you can see, like after 1 generation, after 10 generations, this green one is like shaping like this. And after 100 generation, the blue one is looking like this plot over there. What is the true values? The true values is this black one. That is very bad if we go to the left, and very good if we go to the right. And actually, that's the optimal solution for this simple problem, that if you are in any of this state, try to go to the right, because the right side value is higher. If we just get argmax of the next state, we just can simply solve this problem by going to the right. And kind of our algorithm get very close to true value by 100 of times of running episodes. And here the considerations was constant step size of alpha 0.1. Of course, if you increase it, the the convergence speed can be faster, but that is crucial. You cannot increase it too much. Usually, if you increase it too much, it can be problematic. That in next slide we're gonna see. Clear? Yeah.
So you said this algorithm was used to find if the policy is good or not.
Yeah, it is.
But from my understanding, right now it's like creating a policy. It's not really evaluating.
So basically, TD0 is for prediction and evaluation policy. Yeah, but it's in this example, particular example, designed to show the evaluation of the policy too. Yeah. So your question is like, it is for prediction, we give the policy exactly, and it is evaluating, right? But if we just, with adding the one step of getting argmax, we can't get the policy, right? Yeah. Yeah, that's the reason that this is just showing the how it can be evaluated, to just present it. Instead of, because if we just give the policy there, then it's not like the convergence, the number of the things to show how it is going.
Consider like you give it the perfect policy.
So you can answer yourself. If we give the perfect policy, what happens?
Yes, it will look like
It's still, if you give the perfect policy, if you present it in different number of steps of the updating value, you can see this, right? Because after one time, you just updated the value for this policy, right? But still, you can again get the argmax and update make it as control 2. So very nice question. Any other question? Did you get what your friend asked? So, like we say, let's say the policy is right, up to there. So the given policy is right, and we know that that's the optimal policy. Now here, based on that given optimal policy, since we have TD prediction, you can see the convergence of the value. Indeed, after 1 iteration, 10 iterations, 100 iterations. Clear? If you have any doubt, any question, no worry, ask. This is because simple. Now next algorithm is getting to be a little bit confusing. Okay, good. I consider you all get the point. So we have some important topics to know that later on we're going to use it a lot also. One of the most important points that you need to know is the function approximation. So later on we have a total chapter to talk about function approximation, and we will move toward the advanced techniques that how we can really use it. But I want to make sure that you really understand what does it mean. So let's say we have a couple of data points on the 2D environment, so that like these can be representing data that we have. You can consider, so these are very important in neural network, machine learning, and those things that later on we're going to plug it into the reinforcement learning. So you can consider we have like, we're going to buy a home, and this is like the price, for example, and this is the size of the home, the house that we want to buy. So how much size is increasing? The house size. The price is increasing too. And these are samples, like the house X that is in somewhere that you know that the size is this, price is this. The other one, the other one, the other one. So these are the data that we have. So after having the data, what we can do, we can have linear or nonlinear approximation function that approximates this data for us. What does it mean? It means that, who knows, who don't knows, what does it mean? Everybody knows? Okay, what does this line mean? Somebody tell me, please. Not you. So what is this line? Huh? Regression, but why we have it? How we can use it? That's very simple. We have some data, and these are for homes. This is like, for example, this is like the size of home, this is the price. And I have a predicted model, linear predicted model. And what is this used for? How can I use it? So you need to read a lot and practice a lot then. So if I have new data here, I have new data here. Then I can predict, for example, if I have this size, I can predict the price. You don't know new data price. You know a house that is 100 or 20 square meter, 30 square meter based on, you get the data based on this line, you can predict the price based on the previous information that you have. Right? Very simple. So we have data, we're trying to find the best fitting line as prediction line in order to use that to predict other new data that we have to say, okay, what can be, guess the price. So for example, if I give you the data roughly to you, and I suddenly ask the price of the other home, that's not easy to predict for you. But if you have this line, you can plot it, put it here, look at here, and then say, okay, the prediction is over there. Like the price should be around this one. And how accurate your model is based on your data, your prediction is more accurate. This is the most basic, simplest understanding of the prediction in any model of the like function approximation. Clear? Everybody over there, clear? Okay, good. Because if you don't understand this, after next lesson, you're gonna be in trouble. Because we're gonna move to bring those concepts all into reinforcement learning. So it can be linear like this, it can be non-linear. So because we can have a line like this to predict more accurate. So that if it's non-linear, we can have more accurate prediction over there. So we call it, it can be used to prediction, to use function approximation. We can have linear regression or artificial neural network or any model that can give us this line, right? And based on that background of understanding, we want to have a look first at the one of the metrics named root mean square error. So root mean square error is a standard approach to measure how well my model is doing. I'm asking you how good this is. How you can answer me? How good this is? Why if I draw a line like this, that one is better or this one is better? In order to answer that, we need to have standard approaches. That one of them, there are multiple. One of them is RMSE, root mean square error. That it is using this simple equation to calculate the differences of each one of the points by this prediction line in order to say how good my predicted model is. How much closer these lines are shorter, my prediction is better, right? Because like for the true value, this one, I give the size to my model, the prediction will be something different. Even though I have the true value, my prediction shows something different. This is error that I have. But actually, I'm generalizing the solve whole problem. So this is called RMSE. That is the square root of the sum of the differences between the mean and each one of the items over number of items that I have. So this gives you one value. That value indicates how good your model is, and based on this, you can compare different models. Why we talked about this suddenly? Because we're gonna compare it in the next slides. We want to see the Monte Carlo algorithm differences with the temporal differences. So, before talking about this, any question here? Should be crystal clear for everybody? Must be, actually. All right. So after knowing the RMSE, now what we can do, we can use the same problem, random walk, and compare the temporal differences with Monte Carlo approaches with RMSE. So here you can see different number of walks or episodes, and here, as I remember, yeah, the RMSE error, exactly. And we run Monte Carlo with different learning rates. The Monte Carlo algorithm that we already seen with different learning rates. For example, alpha is 0.1, 0.01. Here, alpha is 0.02, alpha 0.04, 0.03. And with changing different learning rates, you can see that the convergence is like quite different, but generally is lower than temporal differences methods. Temporal differences methods with also the same different also alpha as learning rates have better convergence over there. So of course, as we discussed, that Monte Carlo also can find the optimal solution finally with adjusting the parameters well. So this is just one example. If you can adjust the parameters well and continue it enough, fair enough, it will be converged too. But temporal differences doing well job. But we have multiple points here. One of the points is that by looking at the alpha learning rate, you can see maybe alpha learning rate is faster. You see that it converges faster, this one here. It is converging faster because in the left and comes down quickly. But after some time, it is not doing well. But the other one is slower one, 0.5, although it is not converging fast, but does very good job after some period of time. This is the rule of learning. Not only is not limited to our course here in machine learning, artificial intelligence, or any algorithm that is going to have learning techniques, neural networks, deep neural networks, that you need to change different parameters, try different parameters to see which one is doing better job in learning. And what does that mean? It means that how fast we are updating our value based on the new values that we have. Have a look here on the equation. Here alpha says hold this term, how much impact has on the value, how fast I'm going to update my value. Okay. Oh, I had the equation here. Any question? I'm looking if I explain the important elements that we don't miss anything. Here in this plot, if you have a look at the book, also you can see that it's indicated by the differences RMSE between the value true value function that already considered we have it, like for the random walk that we already have it, right? We know like it's like this, because that problem is very simple. We know if you go to the right what happens, and we can have the ground truth of the value. Any question? Okay. Now we are going to talk about the third algorithm, temporal differences, lambda, TD lambda. We say if we want to update value before end of the episode, like TD1, and use more than one step ahead of TD0 for our estimation, what we can do. The idea is like not doing in one step of the update, also not doing it up to end, somewhere in middle, or taking out some rules to help to update the values in middle of the way. What can I do? The solution is the TD lambda, and is kind of calculating some simple masses to see how effects should be applied on different values during the episode change. So we have two types of implementation for this manner. One is the forward view, and second is the backward view. The forward view is not directly implementable, and it's kind of a little bit challenging and complex, but the backward view is more simpler and better to understand. Both are doing the same thing, and the results of both are same. They are proven also. Because of that, we also are going to only talk about the backward view. So it means that during the episode, each step that I am going, not only I am going to update the value of two steps, consequent steps, but also consider the other updates for other values of the other states. But in backward view, when I'm moving backward, updating the backward is like having the tail. I also have stated that in chapter 12, in Richard's book, you can see the proof of why they are same, and they are both working exactly the same. So in backward view, first of all, updates of the value at each one of the states are happening. So after each step in episode, it takes updates of the all prior steps. So when we are evaluating values during time, all previous ones is going to be updated, but with different impacts that we are going to introduce new variable in order to do that. Then the question is how we can weight or assign credit to all prior steps approximately. In order to do that, we are using eligibility trace, or ET, that is new kind of calculations in order to be able to see how much we can credit or value, better to say credit, how much credit we can give to change the values. Okay. Let's have a look how we can calculate the eligibility trace. We say it increases the frequency of the entering state S at time t denoted by ETS. So we show eligibility trace as ETS. And of course, we need to use and declare more variable to do that. That is like we are using a little bit more memory in order to save them. And on each one of the steps that we have, the eligibility trace for all states decay by lambda and gamma will be calculated, as you can see over here. What does it say? The equation there says eligibility trace of the S state S can be this term over here if the current state is not the state that we are in, or can be the other second term if the state is the current state. So the rule of the updating and the rule of the changing, depending on which state we are, is slightly different. So that if the state is current state, so my robot is moving in these different states, for example, or I'm going to update the values for different states. If I'm here, current state value should be calculated with different equation, that this equation has also the term added by 1. That shows that it is more important for us. What is it happening over there? We have the discount rate. We have the trace decay parameter. We have the eligibility of the t-1 times S added by 1. So the eligibility trace of the state, and actually the previous one before the update, times the lambda times the gamma indicates how much it is eligible to update, and this will be the weight of the update of the value. We will see how this is happening. So discount factor you already know. We discussed it, the same topic. But lambda is the trace decay parameter. It says that, okay, how much impact should I kind of transit to the next, to the previous ones? How much impact I should give? For example, here, if I say I'm in state T, if I'm in state T and I want to update the value, so ST-1, ST-2, and etc., how much the impact of the update should be like smaller, like this, or for example, quickly decrease like this. And that will be indicated by trace decay parameter. That is value between 0 and 1. So this kind of eligibility trace called as accumulating trace, because it accumulates each time the state is visited and then fades away gradually when the state is not visited, because the eligibility trace takes it under the consideration, because all this calculation will tell us how much it should be. That is, we're gonna see it in a second in next slide. Here you can see what is happening, number of times to visit to the state, and accumulated eligibility. You can see that it is increasing and decaying. After again visiting, increasing and decaying, increasing and decaying. This is kind of calculation of the not only distribution simply like this, but also considering how many times I visited each one of these in order to update the value of each state. How many times I visited them. So the trace rate indicates the degree of which state is eligible for undergoing learning change should be reinforced over the inter-docker. That's the same sentence now I just explained to you. So if you have a look at the figure, TD error of ST added by 1 is going to be distributed on the previous ones, ST, ST minus 1, ST minus 2, ST minus 3. Of course, it is going to decay, but also based on the eligibility trace that we've seen how to get the eligibility trace, but we will see how to update each one of those two. So we say eligibility trace assign credit to each state, both with how frequently visited the state and how recently we visited the state. That this comes from the term that in next slide we will see. And at each moment, if we look at the TD error, we are assigning it backwards, as you can see in the figure, per each one of the period states according to the eligibility trace. So to understand it better and clarify for ourselves, let's have a look at the algorithm. Keep this in your mind that we have discounted rate, gamma, lambda trace decay parameter, and the delta as TD error. Delta, TD error, is the thing that we're gonna calculate now in order to use it to update those states over there, the key idea. So what we do, first we initialize value arbitrarily, and the eligibility trace of the state is as 0 for all of the states. So we initialize them as 0. Then we want to repeat for each one of the episodes, initialize the state t per one of the states of the episode, and as initial one. Then we repeat for each one of the steps of the episode by first taking the action from the policy that we have. Policy is given because we have prediction. Take the action. So when I'm saying take the action, you should know that. For example, we had a problem like this. Then we have the environment, and already like this is left, down, for example, right, left, up, whatever it is. We take we generate the episode, then from the episode we take each one of the actions. After taking the action, putting in 80, what we do, we run the action, observe the reward, and next state, ST added by 1. After doing that, we calculate the delta. Delta is the update rule that we have, the R, the TD error that we have, the reward added by the discounted differences between the next state value and current state values. After calculating the delta as TD error based on the reward and differences, what we do, we update the eligibility trace of the state t by adding that we visited this state. We visited the state t, and we say, okay, since we visited the state t, the eligibility trace of that state will be increased by 1. Okay? Then, as I mentioned already, after visiting the state, all previous states at that episode will be updated by this term over there. That we say, value of the ST is equal to adding the value of the ST by the learning rate, alpha, times temporal differences that we calculated here, TD error, times the eligibility trace, So these three elements shows me how much I'm going to update the value of that particular state. That particular state can be like when I'm here, all the past ones can have different values to update it because of the number of times that we visited that state, because of the TD, the amount of TD that we calculated, and the alpha as learning rate. So actually, what is more important here? The most important part here is the eligibility trace of that state, how many times we visited that state. So this is called as propagation of the current information in the past. So that you can see this guy at state tip added by 1 propagate. The idea is, okay, if I am calculating some value here, the intuition is that if I'm calculating a value for this state, why not to update these other ones too? Because this is neighbor of this guy, right? This is the state that is close to this state. So why not update the values of the other states too? We can use only one step to update those. So to updating, we can use this term over here. So after updating eligibility trace of that state, the value of that state, we need to also update the eligibility trace of that state based on the this simple term here, the gamma lambda eligibility trace of the ST. So new eligibility trace of the ST is equal to the multiplication of these three elements, gamma, lambda, previous eligibility trace of ST, so what is this trace decay lambda is doing actually, it was like on the name of the algorithm, is the key point that says, okay, let's kind of determine the credit that I have to update my eligibility trace of the ST, so that in next round this will be used here to update my value. After doing it, I have questions here for you guys. So what happens if the value of the lambda is 0 there? Yeah. Then we have TD0. Because if the lambda is 0 here, then this term becomes 0, right? Completely. That term. Right? Then if this term is 0, then each time eligibility trace is not updating over there. And what is happening over here? We have similar term to the TD0. On the other hand, what happens if the value of the lambda is 1? We have TD1 or Monte-Carlo-like approaches. The behavior looks like Monte-Carlo. Because then the update of the values will affect all of the exactly similar to Monte-Carlo approach. So after that, we update the state. This should have been 1. State, we add it to the next state, and until the state is terminal, we can continue it. When it's terminal, we can terminate the algorithm and it finishes. So we have a couple of points, useful points to know about it. We say almost all of the TD methods can be combined with eligibility trace algorithm. For example, Q-learning or SARSA 2. As I told you, next lesson we are going to talk about algorithms, Q-learning and SARSA. We will see the most basic and the most useful technique of how to implement them. And also we will solve some problems in practice. I will introduce some simulations for you. But there I'm not going to implement eligibility trace. That's the point that you also can, or we also can, merge eligibility trace with Q-learning and SARSA and then compare and see how better it can do in solving our problems. So let's have a look at these plots. These plots again given by your book that compares the Montecarlo and temporal differences, so that by looking at this, in Montecarlo, the amount of change that you can see, the suggested change, although it is happening. So these are different states. It is written situation, better to write state, but so being at different situations, but they are actually the states. And the update for values. So this is the values that we currently have, whatever it is, one current values. Then the Monte Carlo approach suggests change of the value over here to here. That is, this is actual value. Then you can see quickly tries to converge to the actual outcome. But the point is that, although in this example it quickly goes to the actual value, but the point is that we needed to wait until end of the episode. On the other hand, temporal differences or TD control gives you small suggestions of the change for value until converge. So for example, for this one says, okay, go up there. For this one even gives wrong value. For TD is not guaranteed that always the improvement is toward the actual value. Maybe do wrong steps. And later you're gonna see that even these wrong steps maybe can be useful. Not, although we can see it is here totally wrong, but sometimes these wrong steps are also useful in order to explore better. Then here, for example, this amount of change, this amount of change, but finally also this TD is converging to the actual outcome either. Any question? Is everything clear? So we have different techniques of the TD. One of them is SARSA. SARSA is state action reward state action algorithm or technique that combines both of the Monte Carlo and dynamic programming methods again. And the update equation it has similarity to Monte Carlo equation with some differences. That differences is basically is replacing, although it is replacing the GT with the updating the Q of the next state and the action. That this Q, YQ, because we are from prediction moving to control, and in control we are considering Q and the value per each action at each state. Because of that, we don't have value anymore. We have Q, and Q of the state added by 1 and action added by 1. So that update rule is based on the still temporal differences, but this is not the whole equation of the update rule for temporal difference. It is based on the Bellman equation that we will see it in detail in next chapter. So this is part of just the update part. So as a last topic for this chapter, we have bootstrapping and sampling. So as I explained already to you, when you estimate the value based on the another estimation value, so estimated value based on another estimation value, we call it as bootstrapping. What does it mean? It means that, for example, here, the Q of the ST added by 1 and the action added by 1 is another estimate that we already have done. This is another estimate that we read it in order to update something. So that's called bootstrapping. And this term is like related to SARSA. I'm not explaining now. Next chapter completely we will discuss it. Also we will see pretty nice examples. So which one are the techniques based on what we've talked are using bootstrapping now? We can say, okay, temporal differences of course is using bootstrapping. And dynamic programming also is using bootstrapping. But do you remember why? The algorithms that we studied at the beginning as dynamic programming? Who remembers why? Because of the update rule. If you flash back in your mind, the update rule that we studied for value pi s was looking like this, that it had a term over there that coming from value pi s prime. That this was already another estimation, right? Because this was another estimation to update estimation, we call it as bootstrapping. Due to that, dynamic programming algorithms that we've seen also are bootstrapping techniques. And that's the proof. Okay? On the other hand, we have sampling. Sampling techniques means that when you estimate estimation value does not use any other estimates, and it uses the sampling of the whole episode. And that's called sampling technique with GT, that Montecarlo, or some of the techniques of the temporal differences. For example, TD1 is based on the sampling. Clear for everybody? Okay, good. So these concepts all are going to be used, and we are going to build advanced techniques based on these basic concepts of the reinforcement learning. As I told you, these are very important topics that we need to understand. So if I want to summarize this chapter, we talked about the temporal differences first, then we talked about the TD1 technique. We saw that using this term over here, we can update the value. Then we talked about the temporal differences 0, that this term over here we've used for updating the value. And actually, since these were like the prediction techniques, we have already policy, and we have to try to converge and update the value. On the other hand, we saw the temporal differences, that in temporal differences, I showed the most important part, again, for prediction tasks, that we calculated the delta, the temporal differences, the equation, then we used the eligibility trace, and this eligibility trace has been used in order to update the value, and the decay of the eligibility trace during time would help us to implement the technique that we have. So for today, we've seen 3 algorithms. Of course, the third one was the more complex one. I implemented for you guys. I will go to show you the code implementation example. Then you can see how it is working. Later, I will tell you what you need to do. Any question? Okay.